equilibrium of rigid bodies. So if you have a force with a bunch of, actually I can bring the picture I have from, if I can find it. Not a picture that I cannot draw myself, but it's, I guess, nicer to just have it from textbook. So the rigid body, the main difference between a rigid body and a typical body is that the reason we emphasize on rigid because a rigid body is a body that when it's subjected to some external forces, the distance between any two points does not change after applying the force. And my example, remember back then, was a rubber. If you have a rubber, stretch it, the distance between two given points on this rubber, if you look at that, it increases if you stretch it. But so that means rubber is not a rigid body, and that's why we put specifically rigid bodies and not just bodies, because bodies can be flexible. If you're a flexible body, then the story is different, and that's where you are going to deal with them in. You're going to deal with them in solid mechanics, like mechanics of materials, the core solid mechanics. So we're dealing with rigid bodies, meaning that the shape, the bodies do not deform under the forces applied to them within the scope of this course. Right? So we are not worried about deformity or the shape changes, or the if you apply force, the distance between scientific explanation or not scientific explanation. Technical definition would be when we apply force to it, the distance between two specific points on the body stays constant, right? Before and after applying the force. That's basically the general way that we define a rigid body and the way we distinguish that from a flexible body. Now, if you have a rigid body like this, a bunch of forces applied to it, we have a bunch of coupled moments, and we want to study this, right? We use what we learned when we're talking about moments for a while. We know how to find the resultant force. We know how to find the resultant moment. Now, what do we add to this? Only thing we add to this is that we have to draw the free body diagram now for rigid body, which is a little more technical, and we'll talk about that. There's some element added to those four forces that we're dealing with. Remember, we said forces were spring force, cable and pulley, smooth contact, and weight, right? These four forces. And when we come to rigid body, there's going to be another force we'll talk about. But you add free body diagram and Newton's first law to what we learned from before. Newton's first law tells you all the forces. You draw the free body diagram and see what forces do you have there. So far, I've been giving you the forces on a body when we're talking about moments. You draw the free body diagram and figure out the forces on the body. Once you draw the free body diagram and have the forces, it's like what we were doing in when we're talking about moments, right? You find resultant force, resultant moment, right, about some point, given point, and then apply Newton's first law. Since it's an equilibrium, the summation of all the forces should be zero. Added to that, the summation of all the moments also should be zero. So your resultant force and resultant moment should be equal to zero. So let's put it this way. Consider a rigid body subjected to an external, supposed to be an external, well, not, I guess it wasn't even need external forces because we can have multiple forces. To external forces and couple moments. Right? Those moments are free vectors, can be anywhere, force applied to specific points. So when we are in equilibrium, Newton's first law, remember we're talking about particles, summation of all the forces should be zero. Now added to that, so let's just bring that up, the two things, sum of the forces which basically is the resultant force we were calculating before, acting on the body is 0, right? Meaning that the resultant force we calculated before, which basically was summation of all the forces, vector sum, should be 0. Comes from Newton's first law. Added to that, this we already had, the first one we already had when we were dealing with particles, right? This is nothing new. We were finding all the forces and we were saying resultant force is equal to 0. That's condition of equilibrium. Now, added to that, now you get something new. That is some of the moments about, in this case, let's say point O, but can be about any point. About point O is also 0. So what I'm saying is that the resultant moment you've been dealing with, trying to calculate, that is about point O, at about point O, is equal to summation of moments about point O. So you can think about I about point O, I to n. I could write this also as I to n being the whole number of forces, should be 0. So again, whatever we had in particles, we had this one before, right? And when we were dealing with particles, we said, well, let's draw a free body diagram, put all the forces there, and then Newton's first law tells us the since we're in equilibrium, the resultant force should be 0. So we could get equations and solve for those. Remember, in three-dimensional space, we were getting 3 equations: one in I component, x direction, one in y direction, one in z direction. Now, some of the moments about point O now is 0 when we're dealing with a rigid body, because moments come into play, because a rigid body is basically a mass distributed in a shape. So a rigid body, another big difference between a particle and rigid body. Particle is an idealization of rigid body. It means it's a concentrated mass. We don't care about its shape. The rigid body means we have a body, we have a mass, we also care about its shape, right? The force applied to this point has a different effect compared to the force applied to this point. Depending on the direction of the force and where it's applied, you might get moments. It's different from particle, right? And that's why this second part comes into play. Still Newton's law, the derivative of that, it says the resultant of all the moments we were calculating about a point, that should also be 0 for a rigid body in equilibrium. All right. So the process is we start from rigid bodies. We draw the free body diagram, the same process we're doing with the particle, right? We draw the free body diagram for a rigid body now. We isolate the rigid body. We draw the free body diagram representing all the forces. Remember those 4 forces we talked about: the spring force, cables and pulleys, could be ropes or chains, smooth contact, or you can think about it as normal force, and weight. Right now, weight in a rigid body is going to be applied on the center of gravity, which I tell you where that point is. Till end of the semester, we get to figure out how to calculate center of gravity. For now, I'll give you where it is. So weight, these 4 forces, plus what is new when you draw the free body diagram for a rigid body to apply Newton's first law, these 2 equations, is you have to now deal with support reactions. All right, so let me put things together. So we have to draw the free body diagram, right? Free body diagram. You can think about that. Let me put a few words to apply the equations of equilibrium, equations in the previous slide that we introduced, basically coming from Newton's first law, equations of equilibrium we need to let's put it this way, we need a complete specification of all the forces. We need a complete specification of all the known and unknown forces, right? Or we have to say external forces to be more accurate. Unknown external forces that act on the body, right? So we have to draw the free body diagram. Remember, when we wanted to draw the free body diagram, we had to isolate the part, in this case, the rigid body we're looking at, put all the forces on that rigid body, right? Isolate it, draw a line, cut that part cut it out of its environment. Whatever force that is applied, external forces that we cut through, we have to put it there. And so forces, if you remember, just as a review, we introduced 4 forces, right? We said we have springs, or we have springs, we have cables and ropes, cables and we say cables and pulleys, but that includes ropes, chains, wires, whatever that can handle tension. Smooth contact, smooth contact, and weight. And in this case, we put the weight on the center of gravity, because a rigid body is not just a point. You have to figure out where you want to put the weight. You put it on the center of gravity. Typically, I'll tell you where center of gravity is until we get closer to the end of the semester and we start learning how can we calculate the center of gravity. Some center of gravities are pretty straightforward and obvious, like if you have a ball or a rod, center of gravity is exactly in the center, but sometimes it's not clear, and I'll tell you where to put it. Now, smooth contact, when we were talking about a particle, just a small object, the mass, concentrated mass, when we don't care about the way it's distributed in its geometry. Smooth contact was the only kind of contact the particle could have with its environment. But when we come to rigid body now, the way we can constrain the motion should be expanded. And we're going to have another force added to these 4 categories, and it kind of fits into the category of a smooth contact. Smooth contact is one type of that kind of force we're going to talk about, and that's support reactions. And I want to add it right here, and support. Why am I writing it? So this is new, and specifically I'm writing it a different color, and support reactions. Now, what is a support reaction? Well, support in a rigid body basically can be 2 types. Well, there are multiple types, but they can fit into 2 categories. The type of support, and by support I mean whatever, something that the rigid body is in contact with, and because of that contact, the motion, the possible motion of this rigid body in 2-dimensional space is limited. It's been constrained. Right? What are the possible motion a rigid body can have in 2-dimensional space? Can someone tell me? If you think about XY plane, and you have a rigid body like this, what are the possible motions this rigid body can have in this plane? this 2D plane. All right, so if you have it, go ahead, Santiago.
Oh, I was gonna say it can move positively or negatively upon either of the axes rather.
That's true. So it can move this way and this way, either this way, or can move in this direction, right? Up, down. Any other motion, if it goes in an angle, it's basically a combination of motion in the X and motion in the Y, right? With these two, you can go wherever you want on the plane, as long as you can move in X, positive, negative, and Y. So two directions. And since it's a rigid body, it can also rotate, right? That's the added motion. This is also rotation. So there are three possible motions for this rigid body. Right? It can go up and down, left and right, left or right, and then it can rotate. Any other motion is a combination of these three. So there are three possible motions. Now, a support reaction is a kind of force that we have to take into account when we are drawing a rigid drawing a free body diagram. That the specific support or contact the rigid body has with its environment is limiting that motion. All right, that was a convoluted way of saying it. Let's try it again. So if in an example of a smooth contact, think about it. When you have something sitting on a surface, right? If you have let's say object sitting on a surface, right? This surface is limiting the motion of this object downward, right? I can pull it up, right? I can move it left and right. I can't push it down because of this surface. So this surface is limiting the downward motion of this object. So if I draw the free body diagram for this object, meaning that I take it out and remove this, I'm looking just at the object, I have to replace that surface with a force to make sure that that surface is represented in free body diagram. And that's normal force. That normal force is preventing the motion in this direction. Now it could be any, it doesn't have to be horizontal surface. It could be like this. And we have an object here, right? The contact between these two, we put a normal force because this force is preventing this from moving to this direction. This direction it can move, this direction it can move. So smooth contact is a special case of a support. Right? It supports the object in one way or another. Now, we have to expand this concept of support reaction and look into different types of reaction, possible supports, possible ways that we can limit the motion of a rigid body, right? This X, Y, and rotational motion. So in general, you can think about supports as kind of two types. The type that prevents the translation of the body in X or Y, and the type that prevents the rotation of a body. So every time we remove a support, when you draw the free body diagram just for the object and get rid of the support or whatever is in contact with, we have to take into account the type of motion that support is preventing. All right. So here's what I'm trying to say. Support in general, or supports in general, can be, I'll say type 1. This type prevents the translation of a body in a given direction. A given direction meaning that that direction can be positive X, negative X, positive Y, or negative Y. That's like the translation. So when we remove that, what happens? We have to take that support into reaction on a rigid body. So it basically, what it does, that support, what it does, it exerts force in the opposite direction. So if I have this support, remove it, I have to put a force in the opposite direction. If it's preventing the motion from downward, it's preventing this from going downward. If I remove it, I have to exert a force in the opposite direction of the motion that is preventing that from happening. Right? So this is gonna exert force in opposite direction. Again, smooth contact is a very simple version. You remove the contact, you have to put a force in the opposite direction in a direction that the support is preventing your object from moving in that direction. Now, if the second type could be the type of support that prevents the rotation of the body in a given direction, right? Rotation can be clockwise, counterclockwise, clockwise, counterclockwise. So prevents the rotation of a body in a given direction. That means if you remove that, right, the way we were dealing with translation, expand it to rotation. Now that we are dealing with rigid bodies, we have rotation. We have to take a rotation into account. So that exerts a moment in opposite direction. Right? Expanding a same concept. If we have something that is preventing, let's say I have this, I can't rotate this. It's held by my fingers, right? I'm holding this, so I can't rotate it. If I remove my fingers and I want to draw the free body diagram for this, and let's say the rotation is supposed to be this way or it's supposed to be this way, I have to put a moment here in the opposite direction that my fingers are preventing this from rotating. If my fingers are preventing this from rotating this way, right, it means my fingers are applying some moment in this direction, stopping this from rotating. So if I remove my fingers, this can rotate, but it's not supposed to, right? It's still part of a system. I'm just drawing the free body diagram. So I have to put a moment in the opposite direction to make sure that that moment is stopping this from moving. So every time I remove a support, I have to take into account the type of force and moments that I have to replace that support with to make sure that my rigid body, still is in equilibrium and it cannot move. So a good example of that is, let's look at two simple examples. Right? A good example of that could be this. Let me see if I have. Yeah, why not? Let's bring that one. You can draw it, but maybe it's nicer if I just figure 2. There you go. This is a roller. Imagine you have a beam, part of a structure, a rod. There is a roller there, right? It can roll on it. I do not have my tools here. Let's see if I can use this. So let's say I have this washing, right? If I have this one on top of this, and this is on the ground, this can go back and forth, this can rotate, but this roller, in this case, right, this is the ground, this is on top of that, is preventing this rod or beam, in this case, from going downward, right? It's like a smooth contact. So if I remove it, I have to put a force exerted in the opposite direction to make sure that this is not happening. and it stays in equilibrium. If I don't put any force, then I'm removing this roller or this washer in this case, this can go down. And so on my free body diagram, I have to have a force there to make sure that this doesn't happen. Second example, more complicated one. Instead of a roller, if we have a cantilever support. What is a cantilever support? Now, if you have, I have this again, like my, I have this rod there. I'm holding it from one end. This is this case before I draw the free body diagram. Right? This is this case. I'm holding this from one side, tight. If I'm holding it tight, if you want to move it in X direction, you can't. If I'm holding it tight enough and you're not as strong, less strong, you're applying less force than I can apply on this end. Right? If you're too strong, you're going to take it out. But something is in equilibrium, it's not moving. Right? This means that you cannot move it in X direction, cannot pull it this way. You cannot push it down. You cannot do that. And if I'm holding it well enough and it's inside some kind of wall, let's say, instead of my finger, let's say it's inside the wall, you can't rotate it either. So if I remove this and I want to draw the free body diagram just for this beam, right there, this is the free body diagram. Same story for that one. I draw the free body diagram for this beam. If I want to draw the free body diagram for this beam and take out the support, what happens is that on that beam or rod, I have to put a force upward or downward, depending on what possible direction you can think about. I have to put another force in this way because it cannot move in X, it cannot move in Y, and it cannot rotate either. So I have to put a moment in the opposite direction. If you think about it, I want to try to rotate it this way, and I remove this support. Now I have to put a moment in the opposite direction to make sure that it cannot rotate. That's the story of supports. Now, there are 4 types of supports that we're going to work with in this course, right? The general category was like supports that prevents the translation and supports that prevent the rotation. Now, if you go into details, we can actually classify them into 4 types of supports that you will see in this course in 2-dimensional space. In 3-dimensional space, things are more complicated. We'll talk about it. So here is a table from your textbook, right? Figure, I believe 4. Let me bring it again. Sometimes it's just, there we go. See if I can make it as big as I can. Here is the table from your textbook, listing all the possible supports and what force you have to take into account if you remove that support. And there's also an example there from a real structure. And I'm hoping that from now on, you go out, you look at the structures around you, see these supports. First type is a roller one that we just talked about, the roller, right? It's in a very simple example would be a washer. You can imagine something on it. The only type of motion is preventing from is motion in vertical direction, or wherever the direction is this. If the washer is in this direction, it's going to prevent the motion in this direction. Right? It can move in this direction. If this is horizontal, prevents this motion, but it can still move in this direction. So these types are typically rollers, a rocker, a frictionless surface. You'll see a couple types below. You'll see what happens if you have friction. But if there is no friction, also you're on a surface, there is no friction. The only type of, it's like a smooth contact. Think about it this way. This is a smooth contact you had before. Right? This is going to be this. This is going to be this. You have to replace that with an upward force, with upward forces, so they stop the motion, like stop this beam from going down. So the first type of reaction is a roller, rocker, or frictionless surface. When you remove those, you have to put one force replacing that type of support. And the number of unknowns is just one. There is only one force you put there that you have to figure it out. Right? This is a force. You don't know what that force is. When you put the support reaction in your rigid body, it's going to be an unknown that you have to find out from your equations of equilibrium. Second type would be if you have a short cable or short length, meaning that they can only be under tension. So if you remove them, and let's say if you want to draw the free body diagram for this part, or draw the free body diagram for this part, right here, this right on the right, you have to replace that cable. Remember, cable can only be under tension. Short lengths also is a kind of the type of length that cannot be under compression. So you have to replace them with a tension force, a type of force that is pulling your structure at that point. And also, it's just one force. You know its direction. Its direction is along the cable. So you know its direction. The only unknown is its magnitude. Same story for the first one. You know the direction. The direction is perpendicular to the surface at the contact point. Remember the contact force, smooth contact. The direction is always perpendicular to the surface at the contact point. So if this is the contact point, perpendicular to surface, that would be your force. If this is the contact point, perpendicular to surface, where your object is in contact with the surface. Second case is the same, right? You know the direction. The force in a cable is always along the cable, or in the short length, the same story, and it's always under tension. So if you draw the free body diagram, you have to replace that with the force in that direction. So you know the direction, you don't know the magnitude. Third type is a collar. Right? If you have a collar, a sliding collar on a surface, if it's a smooth surface, no friction, this is important, frictionless rod, frictionless pin. That is basically nothing but a contact again between this pin and this surface, between this collar and the surface beneath it. So you are going to get again a normal force, a force that is perpendicular. You're drawing a free body diagram for this, you're isolating this. So you have to replace that contact. You have to replace that collar type of contact or support, we call it, with a normal force. Normal force is perpendicular to the surface that you are in contact with. So you know the direction, you only know the magnitude. The only thing you don't know is magnitude. So that's why all these three, they have only one unknown, only the magnitude. Remember, force is a vector, magnitude and direction. Frictionless pin or hinge, right? This is the pin is a kind of contact, kind of support that you can rotate around it. Right? If it's a pin, you can rotate around it, but you can't move in any upward or in X direction. You cannot move in any direction. So there is no X or Y possible movement. There is only rotation. So when you remove it, you have to put exert, as we said, exert forces in opposite direction. If you cannot move to the right, if you remove that pin, you cannot move to the right or downward. When you remove the pin, you have to put a force from the right to left, and you have to put a force from, if you cannot move upward, from top to down. If you cannot move downward, from down to top, that direction. Now, you can think about it as just one force with some angle, or two components of force, one in X direction and one in Y direction. Right? It's preventing you from moving. Either you can think about this as two components of one force, or just one force with an angle. And the last one, this gives you two unknowns, right? Two unknowns are either the components of force, Fx and Fy, or just the force, the magnitude and its direction, the angle it creates with some horizontal vertical surface line. Right? There's two unknowns as a force. And the last one that is the one that we were just talking about. It's called support, fixed support or cantilever support. Also, you will hear that. Cantilever is the type of beam that we saw right here. This is the kind of cantilever beam. So it's fixed in one end and it's fixed in every possible direction. So if you remove this, you have to take into account the force that is preventing them from moving in X direction and Y direction. So a force with two components, Fx, Fy, and the moment that is preventing this from rotation. So we have to put the opposite, put the opposite moment on it.